Welcome to Physics 364. I'm Bill Ashmanskas. You're welcome to call me Bill or Dr. Bill or even Professor Bill if you want to flatter me more than I deserve. But most people seem to find it comfortable to say Dr. Bill, which is a lot fewer syllables than Dr. Ashmanskas. This is the lab in which you'll spend most of the semester, and I'm sorry that we have to spend our first 3 class meetings outside of this lab, but we're going to find a way to get you through the learning that you would normally do in the first 3 labs as effectively as possible without being able to be here in person to do the labs. Last year at this time, we distributed some pretty elaborate kits involving little parts in boxes, a little laboratory in a box you could plug into your home computer, and a gigantic kit of parts. So I very much hope that it doesn't come to that this semester. But we do have those materials available just in case we have a few people who need to isolate for an extended period of time and would like to be able to do things from the comfort of your dorm room. So at least one of our first 3 assignments will be done in a circuit simulator that runs in a web browser called Circuit Lab. But we'll also have some exercises during the first few days that involve your watching me go through and doing the lab in our lab classroom using our real lab equipment. And I hope that this can give you the sense that you're almost here doing the lab yourself, and there may even be some benefit to your watching me do the lab and sort of looking over my shoulder as I try to explain what I'm doing. In fact, many students found it useful last year when I did just that and let you look over my shoulder as I built and studied things using the at-home kit last year. So when we're able to work together in the classroom a couple of weeks from now, you will assemble circuits on a thing called a breadboard. I think if you search Wikipedia for breadboard, you'll actually find an explanation for the etymology. In any case, it provides a convenient place to wire up and test circuits. So we'll use this all semester. We also have down here a power supply that we will often use to supply voltages up to plus or minus 15 volts or so, and sometimes a third voltage of plus 5. So this power supply can programmably supply a voltage of your choice with a pretty good current up to about 3 amps. And it serves as essentially an ideal battery, an ideal voltage source. And one key idea we'll explore in the first couple of days is the idea of a non-ideal voltage source, which is sort of like a real-life battery. In around the 3rd or 4th lab, we will introduce this device, an arbitrary waveform generator, which can synthesize a voltage as a function of time. Actually, 2 of them with 2 outputs. This will be one of our most trusted tools. And starting your first day actually in the classroom, we will spend a lot of time with this device called an oscilloscope. In past years, a few students have said to me, my goal for Physics 364 is to learn how to use an oscilloscope. And you will absolutely learn how to use an oscilloscope in Physics 364. So by the 4th or 5th week of the course, this oscilloscope will be your eyes so that you can really see what's going on inside a circuit that you build and want to study or debug. So you'll also find at each lab station, when you come into the lab, a bunch of bins filled with commonly used components. These are the most common components that you'll use from day to day. Then in the back corner of the lab, we have a huge number of additional parts. So there are dozens and dozens of drawers filled with components that will become familiar to you throughout the term. So we intend, and I think we've succeeded in past years, for this course to be both one of the most fun courses you'll take at Penn and one of the more empowering courses. The world around us is filled with electronic devices that nowadays it's difficult for us to live without. I can't promise that you'll come away from this course understanding in any detail how a smartphone works, but the knowledge of electronics and of signal processing and of how quasi-intelligent devices like computers work and how they interface to the outside world that we will learn in this course will at least leave you feeling that the electronic devices that surround us are a lot less mysterious than maybe you think they are now. And I think we'll leave you in a position that if you want to use electronics to take on a project of your own, or if you work in a research lab and that research lab contains electronic devices that you want to understand or to modify, to improve or debug, then I think you learn just enough electronics in this one semester course to feel confident that you understand the big picture and that you can learn more and more of the details as needed from reference materials. So let's get started going through the first lab in video form. Let's start working our way through the first lab, for which the file will probably be updated by the time you watch this video. You can, if you like, read through the text about lab reports. The main idea is that we want to give you credit for going through each part of each lab and thinking about it and going through all the steps and taking the time to understand what you're doing. So just keep that key idea in mind. We don't want anybody to spend time writing up nice polished lab reports. We just want somehow for you, as you go through each lab, to document your thinking to some degree so that you can show us that you did the lab and that you took the time to think about each part. And we especially want you, when you encounter something that doesn't make sense, to pause to discuss it with your lab partner, maybe to discuss it with the other groups around you, and certainly not to hesitate to ask one of the instructors. Usually there'll be 3 of us in the room at any given time. So ask me or Joe's or Mia or Matya if anything doesn't make sense to you. Okay, so the first thing we're going to do is this exercise called beeping out the breadboard. So this is the breadboard. It actually can be detached from its mounting here, and it's sort of interesting to look at the bottom side of it and see the pattern of connection. So you can see a metal stripe going across, and there's a little break here in the middle of it, but there are these 2 parallel metal stripes going across, and here there are 4 parallel metal stripes. And again, notice that each stripe is broken halfway across. And then over here, notice there are these short vertical stripes that are all parallel. And notice that this stripe is disconnected from this stripe. So now if we flip the breadboard over, well, you might have an idea after looking at the reverse side why we put these little jumper wires in the middle of the long horizontal rows. That's so that you don't get confused and think that these holes are always connected to these holes. I mean, they are, because we have this little jumper wire here. But the way the breadboard is built, that doesn't happen automatically. So we'll see in a minute that the idea behind this breadboard is that we use these long horizontal rows to distribute things like power and ground, voltages that are going to be used in several different places in the circuit. And then we use these little short columns, each of which has 1, 2, 3, 4, 5 holes in it, for individual nodes in your schematic diagram, little interconnections. So the first thing we'll do is we will pick up our multimeter, also known as a volt ohm meter, VOM, or a digital multimeter, DMM, or sometimes digital voltmeter, DVM. So this will be one of our good friends. So the first thing we'll do is turn on our digital voltmeter. So here it's in the off position. The next setting is AC voltage, for measuring a sinusoidal time varying voltage. You will almost never do that with the voltmeter. You'll do that instead with the oscilloscope later in the course. The next setting is the volt mode for measuring DC voltages, and we will use that all the time. It'll probably be the most common setting that you use for the voltmeter in this course, but not right now. We're actually going to use the ohm setting, and actually right next to the ohm setting, so the Greek capital omega designates ohms. So just above the ohm setting is a little yellow indication that looks like a circular wave spreading out, and it's in yellow. So that means push the yellow button. So we push the yellow button, it's like the second function sort of on a calculator. And what that does is it makes the multimeter beep if there's a small resistance between the 2 probes, and it's quiet otherwise. So this is useful because then we get an audible indication when there is a connection, and then at the same time we see a resistance reading on the screen. Now, by the way, to do this, we plugged in the black wire. So in low voltage electronics, the typical convention is the black wire is ground, which is sort of a common shared point that we call 0 volts throughout our circuit. And the red wire is the voltage of interest. So if we are measuring either volts or ohms or many other functions on the voltmeter, basically anything except a current, then we plug the red wire into this volt-ohm input. If we're measuring a current, then we plug the red wire instead into either the 10 amp input or the milliamp microamp input. So we'll do that later. And actually, one thing that we'll say again and again about using your multimeter is that it is very easy to blow a fuse when measuring currents with a multimeter. So usually when measuring currents, you want to start on the highest current rating and then go down to lower current ratings over time. But for the moment, we're just measuring ohms, and we're measuring ohms in beat mode. So I'm going to reach over here and grab a spool of black wire, and I already have a little piece of red wire cut to length, so we will just use that. And I'm going to reach over here and find the wire stripper. So all of this stuff will be in the little boxes at your lab station when you're finally allowed into the lab. And then I'm going to cut, I don't know, a few centimeters of wire from the black spool here, and I will strip the ends. I actually don't, let's see, I guess the 22 gauge, 0.35 millimeter. It's the second finest setting seems to be the one that does the nicest job stripping the ends off of this wire that we use for our breadboards. And then this end is called a banana plug, and this end is called a spring clip. There are others that sort of grab like a pair of scissors that are called alligator clips. This is a spring clip. So we've already plugged the banana end into the voltmeter, and then I'll grab with the spring clip the piece of wire. So now I have two ends that are little pieces of wire designed to fit into the breadboard. Then let's try probing the breadboard to see what's connected to what. First of all, if the wires are not touching each other, not touching anything of interest, then you see 0L here, which means overload. So it means it's basically like infinity ohms as far as this thing is concerned. It's a very large resistance, too large for the meter to measure. So OL means overload. Then if I touch the wires together, it beeps and it reads either 0 ohms or sometimes 1/10 of an ohm. Okay, so that's good. Now let's look in sector A on this figure and see what's connected to what. So it seems as if these things are connected to each other. These things are connected to each other. These things are connected to each other. These are also connected to each other, but that's only because of this little red jumper wire which was inserted for convenience. So if I remove that, okay, so this is still connected over here, but if I go across to the other side, there's no connection. So there's still no connection. No connection. Whereas if I put the little jumper wire back, and you will probably want to install little jumper wires like that for your convenience. Okay, then we get a connection all the way across. Meanwhile, if I go from this first row to something in the second row, it is not connected. In fact, I can go to something directly underneath in the second row, and it's not connected. So it seems as if this horizontal row is, well, it's connected halfway across, and this is connected halfway across, and if this little jumper wire is here, then it's connected all the way across. The second row has the same connections among itself. It's horizontally connected internally, but the second row is not connected to the first row. So that's interesting. Then we can go over here, and these things are not connected to each other. Oh, and then I can go next door. So if I put something just to the left of it, it's not connected. I can put something to the right of it, it's not connected. But if I go directly below it, it is connected. And I can go 2 spaces below, so that's all connected. But now if I go across this little gap, then that's not connected. Okay, so that's not connected. That's not connected. Okay, that's not connected. I can move this over here, and now that is connected. So again, the idea is when you're wiring up a circuit, one of these little columns of 5 holes will be a typical node on your schematic diagram. So you can connect up to 5 things together that way. If you need to connect more than 5 things together, you can just use a little piece of wire so that you bridge 2 columns together, and then you can probably connect up to 8 things together. And then these horizontal rows are convenient for things that need to connect all over your circuit, which will typically be a voltage that's supplying power to many components, or the ground voltage that you conveniently label as 0 volts on your circuit. So I think that answered beeping out the breadboard. So if we go over to our little lab write-up, we can say that this is connected across, this is connected across, this is connected across, this is connected across, this is connected down, 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 and so on. and then this is connected down, this is connected down, this is connected down, this is connected down, and this is connected across, and this is connected across. Okay, but notice that this is not connected to this unless you install special jumper wire here. And unless you install a special jumper wire here, this is not connected to this. Now you'll usually find it, you'll almost always find it convenient that this should be connected to this. So there'll be a little jumper wire that you'll probably want to put here and here and here and here so that you can make these connections for convenience. Okay, next we have a little pile of 5 resistors whose values we want both to infer from the markings on the package and to measure with the ohm meter, the digital multimeter's ohm function. It's actually a little bit old-fashioned to have resistors whose values you can read from the pattern of stripes, because nowadays if you look at the motherboard on your computer, you will see that the components used are little surface mount devices that are on the order of 1 millimeter or 2 across, and there aren't any stripes to tell you the value. You just have to measure them or store them in bins in a way that you keep track of which values are which. But you can see there are little stripes on these resistors. The color of the stripes is difficult to read on the blue background. That's an unfortunate property of these particular resistors that we buy. But we can read the pattern of stripes. One thing to notice, most of the time you'll just measure these things, but sometimes it's useful to at least be able to recognize the exponent on the right and to recognize the first digit on the left. That's often significant help. Let me see if I can get this to zoom in on the resistor. So here's our first example of a resistor, and you might just have to take my word for it that, well, actually, we have to orient it the right way. So there's a little bit of extra space on one side, and I think I have it backward here. So you want the little bit of extra space to be on the right. So we have red, black, black, brown, and then there's a little space, and there's a brown stripe. That final brown stripe actually means 1%. These are 1% resistors. So red, black, black, brown means 2001. So that is 200 times 10 to the first power. So that's 200 times 10 is 2,000 ohms. So this is 2 kilo ohms. So I expect the resistance, when we measure it with the ohm meter here, to be pretty close, within 1% of 2 kilo ohms, because the stripe pattern is red, black, black, brown, and then there's a little gap, and then brown. So red, black, black, brown, brown, where I paused to sort of indicate that there's a little space there. Let's see what Mr. Ohm meter says. So now I've let go of my little pieces of wire with the spring clip attached to the volt ohm meter. Also, now, well, I guess once again, I've put it into ohm mode, and there was no need to use the beep function. So the beep function is off, because I think it would just be annoying to have it beep in this context. So I'll grab one end with the red lead and one end with the black lead, and this says 1.988 kilo ohms. So that's pretty close to the 2K nominal value. Yeah, okay, so that's within tolerance. 1.988 is within 1% of 2.0. So it's within the 1% tolerance, and it is indeed 2 kilo ohms, or it's indeed compatible with the nominal value of 2 kilo ohms. So this is a 2K resistor. Okay, so its actual value is 1.988 kilo ohms. We often say K for kilo ohms, so 2K or 1.988K, or in this case even you could say 1.99K. All right, so this is a 2K resistor. The next one we have here is, and again, I guess you'll have to take my word for it. So okay, so I think the little gap, I want to put the little gap on the right. So I think that's pretty good. The wide stripe with the little gap before it is now on the right. And this is brown, black, black, red, and then a gap, and then brown. Brown, black, black, red, brown. Okay, so brown, black, black, red means 1002. So that's 100 times 10 to the 2. So 100 times 10 to the 2 is like 10 times 10 to the 3, so this should be 10K, 10 kilo ohms. So I expect this to be within 1% of 10 kilo ohms. Let's see what happens when we measure it with the ohm meter. Okay, 9.93K, so that is indeed within 1% of 10 kilo ohms. Next, we have, okay, I have to orient it so that the brown stripe, which has a little gap before it, is on the right side. And this looks like yellow, white, white, black, and then there's the obligatory brown stripe. So yellow, white, white, black. So it's hard for me to remember yellow. Let's see, so black, so brown, R-O-Y, brown, R-O-Y. See, if black is 0, then you can skip black, so you say brown, R-O-Y. So Brown, R-O-Y. That seems to be 4, and then white is 9, so it's 499. So 499 times 10 to the 0, because black is 0. So 499 times 10 to the 0, 499 ohms. So it's basically 500 ohms, but 499 ohms. So we expect this to be within 1% of 499 ohms, and we measure 498.3 ohms. That's pretty good. Okay, that seems to make sense. Next one. So I will orient it so that the sort of solitary brown stripe is off to the right. And this is red, black, black, black. And then there's the gap and the brown stripe all by itself. So red, black, black, black. So that is 2000. So it's 200 times 10 to the 0. 200 times 10 to the 0 is 200 ohms. Let's see what the meter says. Meter says 199.6. So that is indeed within 1% of 200 ohms. This one, to figure out which brown stripe is all by itself, I think it's this way. Actually, no, I think it's this way. It's pretty hard to tell. You see, the reason why I think it's this way is because this is brown, black, black, brown, and then brown. So 1001 makes sense. 1100 doesn't make sense because 110 or 1.1. 1.1 isn't a very common value. So I guess I had to cheat to figure out which side has the brown stripe that just says 1%. I don't really like these resistors. The blue background makes them hard to see, and the brown stripe on the right is not very distinctive. Anyway, brown, black, black, brown. So that's 1001. So that's 100 times 10 to the 1, which would be 1,000. So this should be 1K, 1,000 ohms, 1 kilo ohm. Let's see what the meter says. Meter says 989 ohms, or 0.989 kilo ohms, which is, I guess it's just a little more than 1% off. So that's marginally within tolerance. So it's 0.99K, nominally 1K. Okay, so we have measured 5 resistors, first by looking at the pattern of stripes, and then by measuring with the ohm meter. This is by far not the most exciting thing you're going to do in this course, but you know, part of the idea of this first day is to get familiar with the equipment. If you were going to be at home all semester, we would have mailed you the equipment, or you could have come and picked it up. So you'll get a preview watching the video of the equipment that you'll work with, and then I think once you get into the lab very quickly, this will all become second nature. Okay, let's now build our first circuit, which will consist of a 9-volt alkaline battery, a 200 ohm resistor, and a red LED. And we will use this battery holder so that we can conveniently get 2 wires on the end of this 9-volt battery and push it into the breadboard. You should read the surrounding text, but I won't read it out loud to you. So let's take the digital multimeter and we can put it on volts mode, DC volts mode, and then we can take our little battery holder and we'll insert the battery into the battery holder. Now, an interesting thing is, so on a 9-volt battery, the small terminal is positive. You see there's this little plus here. So the small terminal is positive and the big terminal is negative, which might not be what you expect. Now, the funny thing is this connector, this little receptacle has to mate with the battery. So you attach a red wire to the big terminal and I attached a black wire to the small terminal because the big terminal on the battery holder connects to the small terminal on the battery. That's a little bit tricky. Anyway, if you plug this thing in the way that it fits, then you get a red wire attached to the positive battery terminal and a black wire attached to the negative battery terminal. You will almost never use something like this in the lab, except on this first day of class. We will use, well, you'll see in a moment, we'll use a benchtop power supply instead of a battery. Once in a while, we might want to build something that's portable, we can walk around the room with. So in that rare situation, we might use a 9-volt battery. Okay, so I guess the lab write-up says we want to measure the battery voltage. So let's do that. I'll connect the black terminal to the black wire, and I'll connect the red terminal to the red wire, and Mr. Meter says 9.4 volts, 9.36 volts. This thing says DC, it's not a minus sign. If you look closely, try to avoid the glare, it says DC 9.361 volts. From a distance, you might think that this little blob is a minus sign. It's not a minus sign. If I connect things the other way, you can see what happens if there really is a minus sign. Here, I'll connect, just for fun, I'll connect the black wire to the red terminal, and I'll connect the red wire to the black terminal. And then here's what the minus sign looks like. We'll see minus 9.4 volts instead of plus 9.4 volts. But, okay, so there is a polarity, of course, to a battery, and there is a polarity to the meter. 9.36 volts. Turn the meter off so that I don't wear out the battery. By the way, this is the circuit symbol for a battery. This is the circuit symbol for a resistor. This is the circuit symbol for an LED. Okay, let's draw a schematic diagram for a circuit in which the battery, the 200 ohm resistor, and the red LED are connected in series. Here, try to pause and do this before I do it. So here's the battery. So the bigger bar is the one with the plus sign. And this is 9 volts. And then we could put the resistor either above or below. It doesn't make any difference. So we'll put the resistor here. We could have put it down here. It wouldn't have mattered. So this is 200 ohms. But what does matter is we have to put the LED in the orientation where it will light up. So the symbol for a diode, or I guess you could put some little photons to make it an LED. Symbol for a diode or an LED sort of looks a bit like an arrow. So if you try to go through the wrong way, you get blocked. If you go through the right way, you can flow through. That's sort of what you're supposed to think of when you see that symbol. So if conventional current, the Ben Franklin style of current, where we imagine positive charge carriers, is flowing this way, then it can get through the diode. If you try to flow a current the other way, it is not able to get through the diode. So a diode is a device in which current can flow only in one direction. An LED is a special case of a diode that lights up when sufficient current flows through it. So I think we want to wire up something that looks like this. So this will be one node in our circuit. Here's another node in our circuit, and here is another node in our circuit. Now we want to use the breadboard to wire up a physical circuit that looks something like our diagram. So when we do that, let's see if we can make the circuit look something like the circuit diagram. So the battery is playing the role of my voltage source. Let's see. So let me use this row, this little column. I'll use this little column for the top of the battery, and then I'll use this other column over here for the bottom of the battery, and then I'll take the resistor and go from the top of the battery over to another column farther over on the right. In fact, I could probably make this even a little more obvious if I put the bottom of the battery down here like that. You don't have to fret about this too much, but it is nice to build up the habit of making your circuit look something like your circuit diagram so that it's legible to you. So then you can look at it, it's understandable, and if you ask me or Joe's or Mia or Mattia to come over and help you, we can immediately understand what's going on. Now, we have to get the polarity right. A resistor has no polarity, same either direction, but an LED has a polarity, and what you'll notice is that one of the leads is longer than the other. Let me put this down here. Maybe it's obvious there. So one of the leads, so I put this down so that the lead on the top is longer, the lead on the bottom is shorter. So when you pick up an LED, if you stare at it, it's not a very big difference because these leads are probably about 3 centimeters long, and the difference in the two lengths is maybe only 1 or 2 millimeters. But if you look closely, you will see that one lead is longer than the other. So the longer lead is the positive side. Shorter lead is the negative side if you connect the LED so that current actually flows through it. So to get current to flow through the LED, the longer lead has to be at a more positive voltage than the shorter lead. So we will first of all, I'll separate these two leads a little bit with my fingers so that I can plug them into different places on the breadboard, and then I'll push the longer lead. Let me just make sure I didn't mess this up. Yeah, I'll push the longer lead into the end of the resistor, and then I'll push the shorter lead into the little column that we're using for ground. And you can see the LED lights up, and that's kind of exciting. So let's zoom in a little bit. So you see, here is the positive side of the battery. It is connected to one end of the resistor in this little column, this little vertical. Then, over in this other column, the other end of the resistor is connected to the long lead, the positive side of the LED. One side is called the anode and one is called the dynode, and I can never remember which side is called which. Then the shorter lead of the LED, the minus side of the LED, is connected, it's in this column, it's connected to the black wire, which then goes to the negative terminal of the battery. So there you go. We have our first circuit, and notice that I did make some effort to wire up the circuit so that it resembles my circuit diagram. Okay, next let's use the voltmeter multimeter to measure the 3 voltage drops. So there's a voltage drop across the battery. This is more like a voltage gain. There's a voltage drop across the resistor, and there's a voltage drop across the LED. So this voltage gain should equal the sum of these 2 voltage drops. That's Kirchhoff's voltage rule. So I'll put the meter on volt mode, and I'll orient it so that the glare is not in the camera's eye. And let's go. So black lead on the black terminal of the battery, red lead on the red terminal of the battery. We should get about 9 volts. We get 9.01 volts. And I think over time we should get a smaller and smaller voltage from the battery as we wear down the battery. So this seems to be 9.00 volts. Then we can go and measure the voltage drop across the resistor. I'm going to put the red lead on the left side of the resistor and the black lead on the right side because I expect this side of the battery to be a higher potential than this side of the battery. Okay, so I get 6.79 volts. So this is, 6.79 volts from here to here. And then I'm going to put the black lead on the short end of the LED and the red lead on the long end of the LED. And this reads, so across here, this reads 2.195 volts. So 2.2 plus 6.8 is 9, so that's good. So it seems like we satisfy Kirchhoff's voltage rule because this voltage gain equals the sum of these 2 voltage drops. Okay, so that's pretty good. 9 volts across the battery, 6.79 volts across the resistor, 2.2 volts across the LED. So knowing that this is a 200 ohm resistor, we can predict from this voltage drop what the current is flowing through the circuit. There's only one branch in the circuit, so the current is the same everywhere. So this current seems to be, let's see, so 6.8 volts divided by 200 ohms is 34 milliamps. But since this is a lab, we can measure the current directly. We have a second digital multimeter, so we will connect our second digital multimeter to measure this current. Now it's actually a little bit tricky to set up a multimeter to measure current. So we're going to take the red lead of the multimeter and we will put it into the amp input. So we usually want to start on the highest setting, amp rather than milliamp. This is because there's always a chance if you run too much current through the multimeter, too much current through the ammeter, the current meter, that you'll blow a fuse and then you have to remove a couple of screws and go find a spare fuse in the back room, and it's a hassle and it wastes 10 minutes of your life. So it's better to spend an extra 10 seconds and be careful when measuring currents rather than too many times during the semester to have to spend 10 minutes changing a fuse. So then we'll go to the amp setting, and I think it beeps at you if the connection you make with the cables doesn't agree with what the setting is. And I think we might have to do, no, okay, I think this should be good. I've never used this meter before actually. So I think we're in amps mode. Now one tricky thing is to measure current, you have to interrupt the flow of current through the circuit. So you have to force the current to flow through the current meter to measure a current. So the way we're going to do that is I'm going to take this end of the resistor. So at this node of the circuit, I'm going to turn it into 2 nodes by moving this resistor to the left a little bit, moving this right-hand side of the resistor to the left. So I'll take the right-hand side of the resistor. Oh, look at this. The current stopped. The light went out. I'll move this over here. And then I'll put the red end of the current meter on this end of the resistor, and I'll put the black end of the current meter on this end of the LED. So I had interrupted the current, but now you see the meter is rejoining. It's allowing, now current is able to flow. It's flowing through the meter. And you can see we have 0.033 amps, which is pretty close to the 34 milliamps that we calculated. And I think now we can go to the milliamp scale like this, and we see 33.3 milliamp. Okay, cool. So we both predicted from the voltage drop and measured with the current meter the current through this circuit. So this is, we've used a voltmeter, we've used an ammeter. They're actually the same device, they're digital multimeters, but this one we're using in volts mode and this one we're using amps mode, or actually in this case milliamps mode. So it's an interesting fact about making physical measurements in a lab. It's also true of, let's say, measuring things with a measuring tape, physical world. You have to have some rough idea of the order of magnitude that you're trying to measure in order to find the right tool to make the desired measurement. So before you can measure a current, it helps to know whether the scale is, hundreds of amps or milliamps or microamps or nanoamps or so on. I will leave to you the next few steps. Calculate the power being dissipated in the 200 ohm resistor. Remember, power is voltage times current. Calculate the largest voltage you can safely apply across the leads of a 100 ohm quarter watt resistor. In other words, if the power is a quarter watt and the resistance is 100 ohms, then you want to figure out what the largest current is. I guess for that you could say power is V squared over R. Calculate the largest voltage you can safely apply across the leads of a 10 ohm quarter watt resistor. Okay, so we did actually measure the current in our circuit. I guess I'm going a little out of order because I sort of know the steps, and so I'm not reading all the directions. So there's an interesting question: what current do you think would flow through the current meter if you connected the meter in parallel across the resistor? So essentially, well, you have to figure out what voltage would be there. If you make the assumption, which you may not have any reason right now to make, that the voltage drop across the LED will change very little as a function of the current. That turns out to be true. So the voltage drop across the LED will always be about 2 volts for a red LED over a very wide range of current. So then you'd say, okay, there must be about 7 volts across the resistor. If you put the current meter in parallel with the resistor, which you really don't want to do, current meter has a resistance on the milliamp scale of about 10 ohms. So that's like putting 10 ohms in parallel with 200 ohms. 10 ohms in parallel with 200 ohms is only a tiny bit less than 10 ohms. It's approximately 10 ohms. So you see 200 is 20 times 10. So it turns out that 200 ohms in parallel with 10 ohms is about 5% less than 10 ohms. So I guess that's about 9.5 ohms, which is pretty close to 10 ohms. So you would have a pretty big current, like maybe 700 milliamps, which would likely blow the fuse in the ammeter. So that's worth contemplating. So you want to be really careful when you connect a current meter that you're not putting a significant voltage between the two leads of the current meter. I mean, it's not going to be the end of the world. It just means that your current meter won't work until you change the fuse, which is a hassle. One thing we haven't done yet is measure the voltage drop across the current meter while everything is set up here. So let's do that. Let's move the voltage meter so that we can measure the voltage drop across the current meter. Notice I can disconnect the voltmeter and the light doesn't go out. You see, if I disconnect the current meter, the light goes out because the current has to flow through the current meter for the current meter to work. But the voltmeter is connected in parallel with something that it measures. The current meter is always connected in series with something that measures. The current meter is connected in series with what it measures. The voltmeter is connected in parallel with what it measures. Okay, so let's measure the voltage drop across the current meter. So this is about 34 milliamps, and I think it's about a 10 ohm resistance. So we see 65 millivolts. So I guess we can figure out the resistance. It seems like about 2 ohms, I guess, because it's 33 milliamps and 65 millivolts. So I think the lab write-up was written at a time when we used a different brand of meters. So it seems as if the series resistance of this meter on the milliamp scale is about 2 ohms. And then it seems as if the series resistance of the meter on the amp scale is, 7.8 millivolts divided by 33 milliamps. Is about a quarter of an ohm. I think that makes sense. If you want to be able to measure big currents, you want a very small resistance so you don't have too big a voltage drop across the meter itself. Okay, so notice, by the way, the IR drop across this 200 ohm resistor is about 6.8 volts. The IR drop across the current meter is only 0.065 volts. It's 65 millivolts. It's about 1% of the voltage drop across the resistor because I guess it turns out the series resistance of this current meter, this Amprobe AM140A current meter, it must be 2 ohms. So 2 ohms is 1% of 200 ohms. So the IR drop across the current meter is 1% of the IR drop across this resistor. So the presence of the current meter really makes almost no difference to the current or the voltages we're measuring elsewhere in the circuit. And that's generally what you want for a measuring device. You want the measuring device to disturb the circuit that it's observing as little as possible. That's true in this case because the 2 ohm series resistance of the milliammeter is 1% of this nearby resistor. The 65 millivolt IR drop across the current meter is on the order of 1% of other IR drops in the circuit. So the presence of this current meter isn't changing. Well, for instance, you see we could go back to measuring the voltage drop across the resistor. And here the voltage drop across the resistor is 6.42 volts. I guess the battery continues to wear down. Now if I remove the current meter and then I remake this connection by moving the resistor back over, then I get 6.51 volts. So it's a pretty small difference, right? It's like on the order of a 1 or 2% difference. So I think that makes sense because we only effectively change the resistance of this resistor by about 1%. And then there's a second order effect of how does the LED respond to that small change. So let's reorient. I'll just take the current meter away. Actually, I'll put the current meter between the battery and the resistor. So let's do that. I'll put the red end of the current meter on positive lead of the battery. I'll put the black end of the current meter on the more positive side of the resistor as we have things wired up. So we now are back to having, well, now it's down to 33 milliamps flowing through our circuit. And I want to set up the voltmeter so that it's measuring the voltage across the LED without touching the LED because we want to be able to swap the LED. So I'll put the red end of the voltmeter on the far end here, the lower potential end of the resistor, and I'll put the black end of the voltmeter on the negative side of the battery. So the LED is there and we're measuring the voltage across the LED is about 2.2 volts. So we're measuring the current through the LED is about 32 milliamps, but none of our instruments is directly touching the LED. So now I can go swap the LED for a green or a blue LED. And you might remember from Physics 250, or maybe from high school chemistry, that the energy of a photon of frequency nu is Planck's constant times nu. Actually, nowadays we usually say F for frequency instead of nu. But anyway, E equals H nu, or E equals HF, or E equals H bar omega. So anyway, the voltage drop across the LED should be bigger for a higher frequency or shorter wavelength light. So let's see what happens. Okay, so I will replace the red LED with a green LED. So we have 2.2 volts across the red LED. Let's see what happens instead with a green LED. The frequency of green, the energy of green is higher than the frequency of red. So the wavelength of red is about 630 nanometers. Wavelength of green is about, okay, so there's our green. No, the wavelength of red is about 630 nanometers. Wavelength of green is, I think, about 540 nanometers. So we have 2.3 volts across the green LED, whereas we had 2.2 volts across the red LED. So then let's try the blue LED. So blue is a shorter wavelength, higher frequency. So this should be a bigger voltage drop. Blue is more like in the 400s nanometers. So you see, then we have 2.97 volts across the blue LED. By the way, the invention of a blue LED, I think, was a Nobel Prize in Physics invention. And it's actually relatively recently that blue LEDs were invented. And it's the existence of blue LEDs, or short wavelength LEDs, that makes LED displays possible, which are ubiquitous now. And now we have 28 milliamps. So I guess, bigger voltage drop means that there's a smaller voltage. Bigger voltage drop across the LED means there's less of that total 9 volts available to go through the resistor. So then the current through the resistor is a little bit smaller, but not by a huge amount. So one important point we want you to take away from the first couple of weeks of this course is that voltage sources, like batteries, are often imperfect, meaning that just because the nominal voltage provided by the battery is 9 volts doesn't mean that it will supply 9 volts no matter what you connect it to. For example, the battery that starts your car is a 12-volt battery, but imagine taking 12 volts worth of flashlight batteries and putting them in series and using that to try to start your car. Seems obvious that it wouldn't work. Why not? Because a flashlight battery just can't supply the huge current required to start your car. So it will turn out that a realistic voltage source has a voltage output whose value depends on the current supplied by that source. Really a voltage source is supplying power, so it's supplying both voltage and current. So it seems plausible that there's a limit to the power that a given device can comfortably supply. So we'll see again and again in this course that anytime we use a device, in particular a sub-circuit that you build, but in this case just a battery, anytime we use a device to supply a voltage, the voltage that you measure will depend on the current which is drawn from that device. So let's try to illustrate that with this 9-volt battery. Now, unlike the alkaline battery that we used in the previous sections, we are here using a super heavy-duty battery because a super heavy-duty battery has a larger internal resistance than an ordinary alkaline battery. And we want the effect that you're going to see, we want the effect on the battery voltage of the current that we draw from the battery to be obvious and to be easily measurable. So even though the effect exists in any real-life battery, we're going to use this super heavy-duty battery because its internal resistance is large enough to be easy for us to measure. So I will connect this battery as we were using the alkaline battery before, and I'm going to wire up a circuit that lets us, so we'll first draw and then wire up a circuit that puts the battery in series with a resistor whose value we will swap to among several different values. And then we'll use simultaneously the voltmeter to measure the voltage supplied by the battery and the current meter to measure the current supplied by the battery. So the first thing we're asked to do is simply to measure the battery voltage when there's nothing connected to the battery. So let me do that now. We see 9.67 volts, and I guess I can write that down. Okay, now let me draw what we want to connect. So here is the battery, and then we want the ammeter in series with the battery, and then we have a resistor whose value we will swap in and out. So that completes the circuit, but now we need to connect a voltmeter across the battery so that we see the battery voltage. And then varying this resistance will vary the current that we draw from the battery, which will allow us to see how the battery voltage depends on the supplied current. Let's do this on the breadboard. We can plug in the battery here and here. We will start with a 10K resistor, 10 kilo ohms. So that has to come back to the negative terminal of the battery, and it can land up here. Then I'll take the current meter in milliamps mode and I'll put it between the more positive side of the resistor and the positive side of the battery. Let me disconnect this initially so that we don't draw any current from the battery until we have everything wired up. Here's a voltmeter, which we will use to measure the battery voltage. I'm going to use an extra piece of red wire to connect the voltmeter in parallel with the battery so that we're not loading too many clips onto one little piece of wire. Okay, so we see 9.65 volts when there is no current. I'm going to write this down. So I equals 0, R equals infinity, V equals 9.65 volts. Then I'll connect the ammeter so current flows through the ammeter. So now we see I equals 0.94 milliamps, R is 10 kilo ohms, V is 9.39 volts. Okay, then, I see I already made a little mistake here. I really want to connect the resistor in a way that it can easily be swapped in and out. So I'm going to avoid making any meter connections directly to the resistor. Okay, I'll pull out the 10K resistor and replace it with a 2K resistor. Then I'll reconnect the current meter, which is making and breaking our circuit. Okay, so now we see the current is 4.55 milliamps, the resistance is 2 kilo ohms, and the voltage is 9.10 volts. Then I can pull out the 2K resistor, replace it with a 1K resistor, and we have the current is 8.84 milliamps, the resistance is 1 kilo ohm, the voltage is 8.79 volts. Then I'll pull that out and replace it with a 500 ohm resistor. Current is 16.6 milliamps, resistance is 500 ohms, voltage is 8.22 volts. Okay, then I'm going to disconnect the current meter again. Now it's often interesting to So one thing you see is I'm measuring the battery voltage, but now there's a negligible current being drawn from the battery, just a tiny current drawn by the voltmeter. And you can see this super heavy duty battery, I guess just because of the nature of the chemical reaction that powers this battery, is slowly recovering from supplying a larger current. So its voltage is sort of slowly making its way back up. It seems as if there's a bit of history in the chemistry of this battery. That's a little, so the simple model that we use for a non-ideal voltage source will not include any concept of history. So that's a feature of this battery that is a bit unusual. Anyway, you can see after a couple minutes it is back up to 9.5 volts. We started at about 9.65 volts, so it's making its way back up. So that's a detail that we sort of want you to sweep under the rug for this exercise. Okay, let's fill in the data table on the next page. So with R equals infinity, we had 9.65 volts, zero current. Then for the 10K resistor, we have 0.94 milliamps and 9.39 volts. For the 2K resistor, we have 4.55 milliamps and 9.10 volts. For the 1K resistor, we have 8.84 milliamps and 8.79 volts. And for the 500 ohm resistor, we had 16.6 milliamps and 8.22 volts. Okay, so using the supplied graph paper, here's 9.65. At the other extreme, we have 16.6 milliamps and 8.22 volts. Then we had 8.84 milliamps and 8.79 volts. And we had 4.55 milliamps and 9.10 volts. And we had 1 milliamp, basically 0.94 milliamps and 9.39 volts. That actually makes a pretty decent line, something like that. And then we could figure out the slope. So delta V over delta I must be minus 1.43 volts divided by 16.6 milliamps, which is minus 86 ohm. Okay, so we will see later when we introduce the idea of an internal resistance or a Thevenin resistance that this is basically like the internal resistance of the battery, which we'll later call a Thevenin resistance or an output resistance or a source resistance, is basically 86 ohms. So we're on the order of 100 ohm. Okay, so we will see soon that a non-ideal voltage source can be modeled by taking an ideal voltage source and putting this so-called internal resistance, which later we'll call a Thevenin resistance or a source resistance, in series with it. So it's as if your battery were like this little box which contains an ideal voltage source and then a resistor in series. And when there's no current drawn from the battery, or negligible current, then the voltage drop across this internal resistance is zero or negligible, and you measure the full battery voltage, which is 9.65 volts in this case. And then as we make this external resistor smaller and smaller, we make this current larger and larger, and then you can see that the IR drop across this internal resistance is bigger and bigger, so the voltage we measure between here and here gets smaller and smaller as we draw more and more current from the battery. So we'll see that in more detail later. This is kind of a preview. It's supposed to make the idea plausible to you that a real-life voltage source doesn't always supply the nominal voltage. It has an actual voltage which decreases as the current supplied by that voltage source increases. Okay, the next thing we're going to do is measure the current versus voltage for an LED. And this is going to introduce the benchtop power supply, which will be our go-to voltage source for the rest of the semester. So we want to wire things up to look like this circuit diagram. Here is the power supply. Okay, so this looks, we use the ideal battery symbol for this. Then in series with that, we have a current meter, Then we have a 200 ohm resistor to limit the current through the LED, and we have this red LED. And then we want to measure the voltage across the LED because we want the IV curve of the LED. We want to know how does the current through the LED vary as a function of the voltage across the LED, or vice versa. So we want to draw a graph relating the current through the LED, current flowing through the LED, to the voltage across the LED. So to measure the voltage across the LED, we need a voltmeter in parallel with the LED. To measure the current flowing through the LED, we need a current meter in series with the LED. Now you may wonder, well, isn't some of the current, which is measured by the ammeter, actually flowing through the voltmeter? That is a valid concern. So somehow we're going to have to convince ourselves that the current flowing through the voltmeter is negligible compared to the current flowing through the LED. And we will see eventually that the voltmeter behaves as if it were a 10 mega ohm resistor. So if we have a maximum of 10 volts, as recommended in the instructions, coming out of the power supply, then the voltage between this point and this point cannot be larger than 10 volts. It will always be smaller than 10 volts. And if this voltmeter behaves like a 10 mega ohm resistor, then the current through this voltmeter will always be smaller than 1 microamp, right? Because 10 volts divided by 10 mega ohms is 1 microamp. So as long as we can convince ourselves that this current is much, much larger than a microamp, since we know that what flows through the voltmeter will be at most 1 microamp, then we can infer that the rest of the current must flow through the LED. So again, there's this interesting fact about making measurements that a measuring device often to some small degree perturbs the thing being measured. Ideal measuring devices, an ideal voltmeter draws absolutely no current. A real life voltmeter should draw as little current as possible. An ideal current meter has absolutely zero series resistance. So in real life, the series resistance of a current meter should be as small as possible, because you don't want the current meter to disturb the current being measured, and you don't want the voltmeter to disturb the voltage being measured. That means you want the voltage drop across an ammeter to be tiny, and you want the current flowing through a voltmeter to be tiny, ideally zero. Anyway, for this circuit, it is a good assumption that the voltmeter does not disturb the circuit, because we will see that the current flowing through the LED will be milliamps, whereas the current flowing through the voltmeter will be a fraction of a microamp. Okay, let's wire something up on the breadboard that vaguely resembles this circuit diagram. Okay, we'll take our red LED, and remember that the longer lead is the one that should be more positive to make the LED light up. So the longer lead is on top as we're looking at it now. So I will put the longer lead of the LED above, as you see it, the shorter lead, and I'll wire it up so that we use this gap in the breadboard to prevent the two ends of the LED, the two leads of the LED from connecting to one another. Then we'll take our 200 ohm resistor. We might as well verify that it is indeed a 200 ohm resistor. So I'll put the meter into ohms mode. I see this meter is set up to measure current, so it doesn't like that. So I should move this over to here. But instead of doing that, I'll pick up the other meter, which is already wired that way. So I'll put this meter into ohms mode, and then we can measure the resistance of this resistor. We think it should be 200 ohms, and we see 199.5 ohms. That's close enough to 200 ohms. We'll just call it 200 ohms. Sometimes in a circuit, it is helpful to write down the exact measured component values, but since our components for this lab are all 1% tolerance, and we generally don't care about precision or accuracy better than 1%, we can just use the nominal values. It's often easier to use the nominal value. So here is my 200 ohm resistor. I will wire that from the top side of the LED over to a point to the left. Then, while I have the voltmeter in my hand, I will put the voltmeter on the volt setting. And remember, I'm connected between this. The black wire always goes here, but you see this is the volts in ohms place to plug in the red wire. So then I will measure across the LED. So here's the positive side of the LED, here's the negative side of the LED. So the voltmeter is connected, resistor is there, Now we want the current meter. So I'll take 2 wires of the current meter. I'll put the black wire. This way we get a positive current. So if the current flows in the red wire and out the black wire, that's positive as the meter reads. So we'll wire it so things actually work that way. Now we need to create a place to plug in the other side of the current meter. So to do that, I will take a convenient little piece of red wire and clip it onto the red end of the meter. See, it helps to keep the colors consistent so that you don't get confused. So we'll just create a little place over here that will be our positive voltage. Now we have to introduce a new object. So this is the Regal DP832 programmable DC power supply. So we'll turn that on, and you can see that the instructions recommend using the left channel, channel 1. So we will do that. So here is channel 1, and it's wired up to a red and black pair of wires. The wires are twisted together to minimize the loop area for interference by electromagnetic waves passing by or other time-varying magnetic fields. So it's often a good idea when wiring from one place to a distant place to have a pair of wires, one outgoing, one return, and to minimize the loop area for magnetic flux to pass between those 2 wires. So we sort of do that in wiring up this power supply. So here's the black wire. So we need to create a place on the circuit diagram corresponding to the black wire. I guess we might as well just use the same breadboard space that we used, a little column of 5 holes on the breadboard that we used for the lower end of the LED for the black wire, and then the red wire will connect to the red wire on the current meter. So now we have a circuit that pretty closely resembles our circuit diagram. Here's the negative end of the power supply. I mean, to be really pedantic, we could have put it over here. We could do that. I would almost never really be this pedantic, but we could put it over here, and then we could run a black wire from the LED over to that point. Okay, so we could do that so that it really looks even more like the circuit diagram. The perfect is sometimes the enemy of the good. So now we want to program this thing initially to 0 volts. So I pushed 0 volts, and then I can push the on-off button, and you see it lights up green, so this channel is on. And there's at least a course reading of the current. So there's the voltage and a course reading of the current. It says 0 amps and 0 volts. Now let's put the 2 meters where you can see them, and I'll turn on the current meter. Okay, we have a current, well, it should be 0, so you can see that what's really 0 in real life reads as 0.015 milliamps. So it seems as if on this milliamp scale we really can't tell the difference between 0 and about 10 microamps. And what is really 0 volts reads out as 0.6 millivolts. We want to vary the power supply voltage in the range 0 to 10 volts in steps that let us trace out an I versus V curve. So I think I am going to just use, well, first, you can't see my graph yet, you'll see it later. So I'm going to put a point at I equals 0, V equals 0. Then let's try 1 volt. So with 1 volt coming out of the power supply, we see 999.7 millivolts. In other words, 1 volt. We see 1 volt across the LED, and we see basically still 0 current. Okay, so we have 1 volt across the LED, and we still have 0 current. Then let's try 2 volts. Aha! So now with 2 volts programmed into the power supply, we actually see 1.7 volts across the LED. You see, back when we had 1 volt programmed into the power supply, all of that 1 volt voltage drop happened across the LED, and essentially none of it, or a negligible fraction, happened across the resistor. And that makes sense because the current is essentially 0. If the current is 0, or approximately 0, then the voltage drop across this resistor is approximately 0. Meanwhile, it will turn out that this LED, when it's in the off state, basically looks like an open switch. So a big voltage drop across an open switch makes sense. An open switch is like a switch in the off state. Okay, so we go back to 2 volts, and we see 1.7 volts across the LED and a current of 1.5 milliamps. Since 2 milliamps is the first tick mark on my graph paper, I'm going to adjust the voltage up gently till I get to 2 milliamps current through the LED. That's pretty good. Okay, so at 2.13 volts coming out of the power supply, I get 1.72 volts across the LED, so the rest of the voltage drop must be across that resistor. And you can work that out. That should make sense with Kirchhoff's rules. So if we have 2.13 volts coming out of the power supply and we have 1.72 volts across the LED, then there must be, the difference must be made up by the IR drop across this 200 ohm resistor. And meanwhile, our current meter says 2 milliamps. I guess 2 milliamps times 200 ohms should be 0.4 volts. That makes sense. 1.7 plus 0.4 is 2.1. Okay, so for 2 milliamps, we have a voltage across the LED of 1.7 volts. So here's 1.7 volts, 2 milliamps. Let's continue turning up the voltage until we have, let's say, at least 4 milliamps, since 4 milliamps is the next tick on my graph paper. Okay, here's 4 milliamps. So the power supply reads 2.59 volts. The voltage across the LED is 1.77 volts. So 1.7, here's 1.8, so 1.77 volts, so that's like this. And unfortunately you can't see my graph while I'm drawing it. Let's go up now until we see 6 milliamps going through the LED. Okay, that's basically 6 milliamps, and so the power supply voltage reads 3.02 volts. Can't see that with the camera very clearly. So we have 6 milliamps of current flowing through the current meter. And you see, we said that as long as we stay below 10 volts, we can put a strict upper bound of 1 microamp flowing through the voltmeter. And we have here 6,000 microamps. So you can rest assured that all of that current is flowing through the red LED here, all but a negligible fraction. So we have 1.805 volts. So I'll make a mark here at 1.8 volts and 6 milliamps. Then we can keep going up to 8 milliamps. Okay, that's 8.1 milliamps, close enough. And we have 3.48 volts programmed on the power supply. This is 1.84 volts across the LED. So for 8 milliamps, we are at 1.84 volts. Then let's go up to 10 milliamps. So we're adjusting the power supply voltage and we're looking at the current meter. Okay, that's 10 milliamps, 9.999 milliamps. So 10 milliamps, the power supply is programmed for 3.89 volts, and I see 1.87 volts here. So 1.87. Let's go up to 12 milliamps. Okay, 12 milliamps, the power supply is programmed to 4.33 volts, and I see 1.899 volts. So then let's go up to 14 milliamps. 14 milliamps through the LED. Power supply is programmed to 4.77 volts. I see 1.93 volts across the LED. Let's go up to 16 milliamps. Okay, 16 milliamps through the LED. Power supply is programmed to 5.19 volts, and the voltage drop across the LED is 1.95 volts. Let's go up to 18 milliamps. Okay, 18.06 milliamps, call it 18. 5.63 volts is what the power supply is programmed to, and I get 1.98 volts across the LED. We'll go up to 20 milliamps. Okay, 20 milliamps through the LED. 6.06 volts is what the power supply reads. By the way, it also reads 0.02 amps. So that's compatible with the current meter reading 20 milliamps. And 2.01 volts. Let's go up to 30 milliamps. This is getting a little bit dull, so we'll keep going till we get to 30 milliamps. I think I can change, so by pushing this left button, I think I can change which digit the knob is turning. So now I think we can increase the voltage a little faster. So now instead of going up in 0.01 volt steps, we're going up in 0.1 volt steps. So that's useful. So yeah, these buttons left and right move. You can see there's basically a little place where you can see where after or before the decimal point you're setting the voltage. Okay, with the power supply at 8.2 volts, I see 30 milliamps through the LED and 2.13 volts across the LED. So I'll say x-axis 2.13 volts, y-axis 30 milliamps. Let's see if we can get to 40 milliamps. Well, I'm now at 10 volts on the power supply, which is where the instructions said to stop, and we are at 38 milliamps through the LED and 2.2 volts across the LED. I'm going to go a little bit higher till we get to 40 milliamps. There we go. Okay, 10.5 volts programmed for the power supply, 10.3 volts programmed for the power supply, 39.85 milliamps through the LED, 2.25 volts across the LED. So up here, basically at 40 is 2.25 volts. Now I'm kind of curious how to get to 50 milliamps. I'm going to keep going until we get to 50 milliamps. I mean, I'm very gradually increasing the current, so I think we're not in danger of blowing anything up here. 50 milliamps, 12.6 volts on the power supply, 2.39 volts across the LED. So 50 milliamps, which is where the graph paper ends for current, we have 2.39 volts across the LED. So now, once you see the graph, this will make sense. It actually makes sense, I think, for us to go back down to an LED voltage more like 1.5 volts. So let's see how far down we have to bring the power supply to get to 1.5 volts. And we want to see what's happening just as the LED starts to conduct. Well, let's first stop at 1.6 volts. 1.6 volts across the LED. We have 0.45 milliamps, and the power supply is set for 1.7 volts. So at 1.6 volts across the LED, we have 0.4 milliamps. So do we even have, this is 2 milliamps, I guess, down there. Okay, then we'll go down until we see 1.5 volts. Okay, and that's 0.04 milliamps. That is pretty hard to see. Okay, if we went down to 1.3 volts across the LED, then it says 0.02 milliamps. Okay, so now let's look at the graph. So I think I can turn the meters off now. I'll push this button so that the green now is no longer illuminated, so the power supply is no longer supplying voltage. And I'll let you see my graph. Okay, so looking at my graph, you see the current is basically zero, or it's teeny. The current is negligible until we reach about 1.6 volts, and then the current rises rather quickly, even for very small changes in voltage. So if we did this for an ordinary diode rather than an LED, we would see an exponential shape. So we don't quite get the exponential shape for the LED that we would expect for the diode, but you still see this feature that is pretty common property of diodes, and LEDs are a type of diode, that below some threshold, the device is basically off, like an open switch. And then you reach that threshold, and the threshold seems to be somewhere between 1.6 and 1.8 volts. So you reach that threshold, and then the current rises very rapidly, even for very small changes in voltage. So that's why you have to be careful not to put a very large voltage across the LED, because let's say you put 3 volts across the red LED, probably the current would be some huge number. There's a question on the next page. Can you guess what might happen? But don't do it. If you were to put 5 volts directly across the LED, hint, power equals current times voltage. I have never tried this. I'm pretty sure the LED will cook. I'm kind of curious, so maybe this is the one time to try that. Let's see. If I set the power supply for 5 volts, okay, right now we're going through the resistor, so then I don't want to blow the fuse in the current meter, so I'll remove the current meter. So now I need to make a connection bypassing the current meter. Well, here, I'll do that like this. Okay, the LED lights up. Oh, I could turn the voltmeter back on. So I see 1.95 volts across the LED. That's okay. Now, if I were to move this yellow wire, well, here, I can unplug the resistor. I unplugged the resistor. So now we have an open circuit. So if I move this yellow wire over to the top side of the LED, the full 5 volts from the power supply will be across the LED. I think I'm going to get a set of safety glasses for this. Okay, I have a set of safety goggles. I'm going to put on the safety glasses, and then let's see what happens. Well, also, I'm going to turn off the power supply. I'll move the yellow wire over, and then we'll see what happens when I turn on the power supply. So it actually lights up. We have 200 milliamps, 0.2 amps flowing from the power supply. So that's actually kind of interesting. I thought it would burn out. It actually has not burned out yet. Yeah, that's pretty interesting. Let's see what happens if I put 6 volts across the LED. Okay, I still get about 0.2 amps. Let's see what happens if I put 7 volts across the LED. Aha! I think I might have seen it blow out. There's just a tiny little glow now. So if I go back to 5 volts, yeah, so it looks a lot dimmer. Here, let's do 8 volts. I think we basically burned it out. So it seems much dimmer than it was before. So it's not nearly as exciting as I thought it might be. But it does seem that we basically burned out most of the LED's brightness. I wonder what happened at the device level. Here's 10 volts and we see 0 amps going through. Go back to 5 volts. Yeah, I think now I've completely burned it out. With 10 volts, I completely burned it out. So now it doesn't conduct at all. So I go back to 5 volts, we see no current flowing through it. I go back to 2 volts, see no current going through it. I go up to 10 volts, we see no current going through the LED. So, okay, so we succeeded in burning out the LED by putting 10 volts across it. I always wondered about that. Okay, there is only one more part of today's lab. We have these two mystery boxes, box A and box B, and we want to measure the IV curves of these two mystery boxes. There is one subtlety which you can see if you read through the write-up for the mystery boxes, which is if the mystery box has a very, very large resistance, then it may be possible that the current measurement we get will be misleading because some current that we think flows through the mystery box will in fact flow through the voltmeter if we use this configuration. If we use this configuration, then the voltage reading may be misleading if the resistance of the mystery box is extremely small. This will give us an accurate measurement of the current through the mystery box, but you see, if the resistance of the mystery box is comparable to the resistance of the ammeter, then the voltage measurement we measure this way will be misleading. So this setup would give us misleading results if the resistance of the mystery box is tiny, like a few ohms. This setup will give us misleading results if the resistance of the mystery box is huge, like mega ohms. I think it will turn out that neither one of these two issues applies for the mystery boxes that we have, but this is worth bearing in mind. Again, in most cases, the lab instruments will give you a straightforward result, but it is always important to bear in mind the limitations of the lab instruments. And in particular, the series resistance of the current meters that we use are on the order of ohms. Tiny fraction of an ohm in amps mode, in milliamps mode. It's 2 milliamps for the current meter we've been using today. I think 10 milliamps for one we've often used in the past. And a digital voltmeter almost always has an input resistance of 10 mega ohms. We'll see in the reading what that means, but it basically means a real-life current meter looks like an ideal current meter in series with some series resistance. So a real current meter looks like an ideal current meter with a small resistor in series. A real voltmeter looks like an ideal voltmeter with a very big resistor in parallel. So a real-life voltmeter can be modeled as an ideal voltmeter, and then there's some big resistance in parallel with that, and that big resistance is, for every voltmeter I've used recently, 10 mega ohm. So if you're looking at objects in your circuit whose resistance is sort of in the mega ohms range, then this 10 mega ohm parallel resistance, the internal resistance of the voltmeter, matters. And if you're looking at currents through circuits whose resistances are tiny, like on the order of ohms, then this small series resistance matters. So you just have to bear that in mind. You need to know the order of magnitude of what you're measuring to understand the degree to which your measuring devices are appropriate for measuring that phenomenon. So we want to draw, sort of sketch, an IV curve, current versus voltage, for mystery box A and for mystery box B. Let's first wire up mystery box A. Mystery box A unfortunately has some kind of inconvenient connections, so we'll just wire one wire here and one wire here on the breadboard. Then let's use configuration, the configuration on the left, which is the same configuration we used for the LED earlier. It should be fine. So we'll take our current meter, and the red wire of the current meter will go to the red wire of the programmable power supply. The black wire of the current meter will go to one terminal of the mystery box. The other terminal of the mystery box should go to the return, the black wire for the programmable power supply. So this little black wire accomplishes that. Then all we're missing is to measure the voltage across the mystery box. I'm going to trim myself one more little piece of black wire. So I use the second smallest tab on the wire stripper for this breadboard wire. Turns out I already had a piece of red wire, so I will use this pair of wires to make the spring clips on the voltmeter more convenient for plugging into the breadboard. Sometimes you can just grab one leg of a resistor or other component, so you don't always have to go through the hassle of putting little wires on the spring clips, but often it turns out to be convenient. Okay, so the red voltmeter lead is connected to what I expect to be the higher potential end of mystery box A. The black voltmeter end is connected to what I expect to be the lower potential lead of mystery box A. I'll turn on the voltmeter, I'll turn on the milliamp meter, and then let me set things up so that you can see what's going on. Okay, here we go. So I will set the voltage to 0 volts and then turn on power supply. I didn't want to turn it on with the voltage set to a large value because we don't know the resistance of this mystery device and we don't want to risk running a large current through it. So it seems as if at 0 volts we get 0 milliamps. Fair enough. Now let's try 1 volt. At 1 volt seems as if we get 2.1 milliamps. So 1 volt, let's see, 20, 10, 5, seems like that would be about here. Let's try 5 volts. At 5 volts, we get, see in here the voltage that we program into the power supply is the same as the voltage across the mystery box because there is no additional series resistor. So we get 10.5 milliamps at 5 volts. Let's try 10 volts. We get 21 milliamps at 10 volts. Try 15 volts, 5 volt, and we get 31.5 milliamps at 15 volts. Let's try 20 volts. We get 42.1 milliamps. Then we can try a negative voltage. Something interesting just happened. I think, okay, for a reason I don't understand, this power supply just shut itself off. I heard the fan go and then it shut off. Okay, let's try a negative voltage. Let's try, if we go to 0 volts, I actually think this power supply is not able to go below 0. So to get a negative voltage, we need to swap the two ends of the power supply cables. We need to swap the red and black cables coming from the power supply. Let's do that. So here are the red and black wires coming from the power supply. I will just interchange them. Seems as if these wires have been plugged and unplugged into breadboards so many times that we finally experienced metal fatigue. So I'll trim back a little bit of wire and strip a few millimeters of insulation. Okay, black wire goes here, red wire goes here. So now the power supply will still think it's providing a positive voltage, but we will see on the voltmeter a negative number. Let's see if that works out. So 1 volt, and we see minus 1 volt now. That's good. And this is 2 milliamps. Let's go to, well, here it says minus 1 volt, and we have about minus 2 milliamps. Okay, so then we can go to 5 volts. One thing I don't understand is why my current meter is not showing me a negative number. I'm accustomed to ammeters reading a negative value. Okay, I think there's some auto range feature. All right, here we go. Now I see a negative number. Minus 10 milliamps. Good. So minus 5 volts, minus 10 milliamps. Then we can do 10 volts, minus 10 volts, minus 21 milliamps, minus 10 volts, minus 21 milliamps. And we can do 15 volts, minus 15 volts, minus 31.6 milliamps, 20 volts, minus 20 volts, and minus 42 milliamps. Okay, that looks like a pretty good straight line, and I guess we can figure out the slope. Seems as if the slope over here is 20 milliamps divided by 10 volts. So 20 milliamps divided by 10 volts equals, well, it turns out this is the reciprocal of 500 ohms. Okay, so this graph has a slope which equals the reciprocal of 500 ohms. So an amp divided by a volt is a reciprocal ohm. A volt divided by an amp is an ohm, since V equals IR. And we can put the voltmeter on ohms mode and then measure directly across the two terminals of box A, and we confirm this is roughly a 500 ohm resistor, 473 ohms. And then we can look inside mystery box A, I think, and we see, sure enough, a resistor yellow, brown, blue, black. Yellow, brown, blue, black. Let's see. Yellow, brown, blue, black. Brown, ROY. 1, 2, 3, 4. This is 1. Oh, brown, ROYGB. Brown ROYGB. So this is 6, and then black is times 10 to the 0. So that should be 416 ohm. 473. I wonder. I think what I think is brown is actually violet. So this, it's really hard to see on the blue background. I think it's yellow, violet. Yellow, violet, blue, black. So violet, black, brown, ROYG, black, brown, ROYGBV. Yes, that's 7. Okay, 476. Okay, so we measured 474. It's actually a 476 ohm resistor. Well, it's nominally a 476 ohm resistor. All right, let's move on to mystery box B. Mystery box B has one red and one green wire. So I will define a positive voltage across box B to be that the red wire is more positive than the green wire. So let's put and let's go back to positive voltage mode with our power supply. So I'll put the black wire at the black wire and the red wire at the red wire. Okay, so then let's put the green wire adjacent to the negative power supply terminal, and we'll put the red wire at the positive, at the downstream end of the ammeter, which is next to the positive end of the power supply. Again, this is mystery box B, and we'll set up our 2 meters. The voltmeter will measure the voltage across the mystery box. Black wire of the voltmeter goes to the green wire of the mystery box, and the red wire of the voltmeter will go to the red wire of the mystery box. And then here is our current meter. Put the current meter on the milliamp scale, put the voltmeter on the volt scale, and we'll go to 0 volts, and we'll turn this on. Okay, so we have 0 and 0, not too surprisingly. Let's go to 1 volt. So it seems like nothing is happening at 1 volt. Let's go to 2 volts. It seems like we have 0.04 milliamps. So still essentially nothing is happening at 2 volts. Let's go to 3 volts. Now we have 0.08 milliamps. Something's starting to happen, but it still seems like basically nothing is happening. We go to 4 volts, 0.1 milliamps. So as far as this scale is concerned, that's still basically 0. 5 volts. Oh my goodness, now we have 11 milliamps. Okay, that was kind of abrupt. Then let's go to 6 volts. Okay, now at 6 volts we have almost 20 milliamps, 19.5. So here's 20 milliamps, so 6 volts. It seems like we go up to here. So this is box A, and now we're graphing box B. Let's go to 7 volts. Okay, now we have 28 milliamps. That's 7 volts. Then we'll go to 8 volts, and we have 32.5 milliamps. We can go to 9 volts. We have 32.6 milliamps. We can go to 10 volts. We have 32.7 milliamps. Let's go to 15 volts. We have 32.8 milliamps. What if we go to 20 volts? Still 32.9 milliamps. Okay, so it seems like this is a pretty unusual IV curve. It seems like nothing happens until we reach about 4 volts, or almost nothing happens. And then it seems as if the current rises pretty quickly as we increase the voltage. Then we get up to about 7 volts, and the current is pretty much completely flat at about 30 milliamps. I guess we could see what happens if we use negative voltages. Okay, let's try that. We'll go back to 0 volts, and I'll turn this thing off, and I'm going to swap the 2 wires coming out of the power supply. Okay, and we'll turn this back on, and we can do 1 volt. We get no current, basically. Let's see what happens if we do 5 volts. Nothing. What if we do 10 volts? Nothing. How about 20 volts? Nothing. Okay, so this is something that looks very unlike a resistor. This is box B. Interesting. Let's look inside. Okay, I'll go back to 0 volts here. I'll turn this off. I'll turn the meters off. Then we can look inside this mystery box. There was actually an LED among other things. So I think probably one thing I forgot to notice. Here, if we go back to the positive voltage setting and we plug this back in like this, I think when we went to here's 5 volts, turn it on, nothing there. If we go to 7 volts, the LED turned on. So seems like, see now it's starting to turn off. Seems like somewhere around 5 volts or so, the LED starts to turn on, then the LED remains on. So this contraption actually is a 3-terminal device called a voltage regulator. It is a way that you can get a nice reliable 5 volts, for example, from an unreliable let's say a 9-volt battery, or something that you know will be at least a couple volts above 5 volts, but is not well regulated. And then we're using that to power an LED in series with a resistor. So it turns out that the current flowing into one of these devices is the same as the current flowing through the device, the circuit whose voltage is being regulated. So we have this LED whose voltage drop is around 2 volts, and then there's a resistor which looks like brown, black, black, black. So that looks like a 100 ohm resistor. So 5 volts minus this 2 volts is 3 volts. 3 volts divided by 100 ohms is 30 milliamps. So that explains the 30 milliamps we see here. So if you just take my word for it that this device is designed to provide 5 volts between these two terminals, it's called a voltage regulator. So once the input voltage is sufficiently high, then the voltage between these two terminals will be 5 volts, and then 5 volts minus the 2 volts for the LED leaves about 3 volts. 3 volts divided by 100 ohms is 30 milliamps. So you should see a 30 milliamp current flowing once this voltage reaches 5 volts. So that's what happens in this plateau region. But we don't reach that plateau region until the input voltage is about 2 volts higher than 5 volts. That's because this voltage regulator, it turns out, requires an input voltage a couple volts higher than the regulated voltage. So to get a regulated voltage of 5 volts, it turns out you need to supply at least about 7 volts to this thing. And so that's the turn on. So in this turn on region, the output voltage of this voltage regulator is less than the nominal 5 volts. But then once we reach this point, the output voltage is the nominal 5 volts. Then there's a little diode here. The diode is to prevent us from damaging this device if we run a negative voltage across it, because I think this thing is not designed to tolerate a negative voltage. So the diode just blocks current from going the wrong way. So that explains why for a voltage less than 0 you see 0, because this diode will not allow current to go the wrong way. So here the diode is blocking it so current doesn't go the wrong way. Here it's not at all on yet, and then here I guess we're just gradually turning on the LED, but the voltage across the LED resistor combination is not yet 5 volts. And then once that voltage across the LED resistor combination reaches 5 volts, it stays there. That's what this thing's job is, and so then the current is constant. That's pretty complicated. We'll see how that works later in the semester. So that was all of Lab 1, including the optional extra credit part. Whoa. So the real goal of this first lab was to get you accustomed to using the lab equipment, the meters for measuring voltage and current, the power supply, and then just to reinforce the idea that, except for very special cases like this box, a typical voltage source is not a perfect voltage source. So we noticed that batteries, and especially this heavy-duty style battery, are not perfect voltage sources. And we will see that many of the circuit fragments that we build serve as non-ideal voltage sources whose voltage drops linearly as a function of the current drawn. This power supply is a special case. It's designed to supply a perfectly regulated voltage up to some maximum current. So this is one of the few examples you'll see of an absolutely perfect, or for all intents and purposes, perfect voltage source. So that's quite a bit to digest for this first day, and you have a reading assignment for the weekend, which should help you to digest things even a little better. So I think the reading will help you to make sense of what you saw me do in the lab today. And again, what you saw me do in the lab today, I really wish you could do for yourself. There may be time for you to repeat some parts of it yourself, and that might actually go faster now that you've seen me do it. But in any case, what you saw me do today is what you would normally do on the first day of class. And again, the idea is to get used to using the lab instruments, to get used to using the breadboard, and to see an example of a non-perfect voltage source, as well as an example of a non-linear device, a light-emitting diode, that has an IR curve very different from that of a simple resistor. So that should at least give you something to think about and to bring the weekend's reading assignment down to reality.